One of the key concepts behind understanding signal processing is understanding that we can represent signals in the time domain and the frequency domain. Now, you would have done this a little bit in the systems modeling class. So we'll go through a bit of revision to remind us time domain, frequency domain, what they are and how they're used. So I've mentioned there's two fundamentally different ways of looking at the world. One is the time domain, where we're representing signals as they change over time. So we might see the voltage of a signal changing over time, or we might see the distance that we're measuring from a signal changing over time, or we might see the force the signal's providing is changing over time. So we're asking that fundamental question, how do these things change over time? And if you see those time domain graphs here, you'll see that there's different signals there, probably from an oscilloscope or something like that, and they're at different frequencies and they're changing differently over time. Well, the other way to look at the world is in the frequency domain and asking the fundamental question, what frequencies are contributing to this signal and by how much? And so we see a signal composed of a series of different frequencies and how much of each of those frequencies contributes to the final signal. I really like this diagram that illustrates it well, that you see from the time domain, a series of frequencies, and these frequencies may be overlaid over each other. We'll talk about that in a moment, and basically all added together. But then if you look at it from the frequency domain, you can see those individual frequencies and the amplitude of those individual frequencies, essentially how much of those frequencies will make up the other one. And we can actually move from one of these domains to the other domain. We can move from the time domain to the frequency domain. And then we can go back again from the frequency domain to the time domain. And the way we do it is something called the Fourier transform. The Fourier transform is essentially a mathematical transform that allows us to move from our time domain signal and represent that time domain signal as a frequency domain signal. Now, we're not going to go into all the heavy maths about it. I'll show you what it looks like in a moment. But essentially it allows you to take your time domain signal and decompose it into a series of frequency buckets and say, here's all the different frequencies that we're looking over, and here's the amount each of those frequencies contributes to this signal. Now, if we want to go back again, we use what's called the inverse Fourier transform. So Fourier transform goes from time to frequency domain, inverse goes to frequency to time domain. Now, here's our standard form for the Fourier transform, where our xt is our time domain signal that we're trying to convert. So that's our signal in the time domain. And our xf is our Fourier transform of that signal. So we're now in the frequency domain. You can see f is our frequency variable and t is our time variable. So basically we're looking at trying to work out how much energy is there in each frequency for the particular signal x. And that's what we're classifying with our Fourier transform. Now, when we're talking about Fourier transforms, there's a whole lot of maths that you can go into. We're going to bypass most of that maths to give you a fundamental graphical understanding of it, because there's other subjects where this is covered in more mathematical detail. So here we've got both some MATLAB code, but also a couple of signals here. You see in the graphs above, we've got two waveforms. One waveform that's at 150 hertz and one waveform that's at 500 hertz. Now, if we add those waveforms together, it's a process we call convolution, we add them together and we get another waveform. And that other waveform looks a bit weird and lumpy and hilly, but that's basically a result of we just graphically add those signals together, mathematically as well. But if you have a look, when both those signals are low, the output signal is going to be low. When both those signals are high, the output signal is going to be higher. When both those signals are maybe midway, the output signal will be more midway. You can track them through and follow them through. If you want, you can copy all that code into MATLAB and actually see it in action and graph these things. Now, remember, there's three signals here, essentially. We've got our 150 hertz signal, we've got our 500 hertz signal, and then we add the two together, and that two together has both a 150 and a 500 hertz component to it. Well, then we can use, and MATLAB, it's a one-line code to run a Fourier transform, the fast Fourier transform. and that will break it down and show us what these signals look like in terms of their constituent components. And so you can see these signals here are our Fourier transform view of those signals that we had on the previous slide. You can see the first one shows that 150 hertz peak. So we're showing it our frequency or the amount of energy at 150 hertz. Our second one is that peak at 500 hertz. Now you see both of these only have one peak in them because we've only got one fundamental frequency here. In our third graph, this one just here, we see two peaks because we've added those two signals together and we've got two peaks. So now you can see the power of these Fourier transforms where we've got this signal that looks a bit unusual and a bit lumpy, and we've actually worked out, oh, what are the fundamental frequencies within this particular signal? Now, we don't need to just add two signals. We could add more signals. We could add hundreds of signals. We could add maybe 6 signals. And you can see here, we've got signals that we've added together from 150 hertz, 500 hertz, 600 hertz, 725, 900 hertz, 1500 hertz. So a whole lot of frequencies there. We add them all together and we get this weird lumpy mess. It looks like someone walking up and down a hill or something like that. Well, then we pass this final signal through to the Fourier transform and look what we get. It tells us what all the frequencies are within this weird lumpy mess. And so we can identify, okay, there's that frequency and that frequency and that frequency and that frequency, and we've added them all together to get whatever final waveform we've got. Now that can be super useful for multiple different reasons. We could be wanting to filter out certain frequencies. We could be looking at what's the magnitude of certain frequencies, how much are they contributing to our system? But essentially, what we can recognize with these Fourier transforms is any signal that we want to create, we can create it by adding together a series of sine waves and cosine waves. Don't believe me? We'll have a look at this. Imagine a square wave. A square wave is basically a wave that goes like this. It looks like a series of squares or rectangles. And, well, they've got nice sharp up and downs, which look really nothing like a sine wave, do they? Well, what we can do to generate this square wave is we can add in what we call successive odd harmonics of the sine wave. So if our sine wave is at 100 hertz, the next odd harmonic of that is at 300 hertz. So we add a smaller version of that. We add a third of that signal at 300 hertz. And then we add a fifth of the next odd harmonic, which is at 500 hertz. And you can see that we're getting something that's approximating a bit more like a sine wave with each successive odd harmonic that we add. Now, if we add lots of them, we get those really sharp curves. We add even more, well, it'll get sharper and sharper until those ripples will decrease and it will look essentially like a square wave. Now, if we run the Fourier transform on that, we could look at that in the frequency view and see at the top there, all of those different harmonics from the first one, which is the fundamental one at 100 hertz, through to all the other ones we've added in there, which allow us to create something that removes a lot of that ripple and looks a lot more like a square wave.